But morning, everybody. So welcome everybody to our second TWED of the fall 2025 season. Let's hear it for TWED. Let's hear it for Abraham Sander. He's going to be giving us a great talk. Just a couple of logistics. We are recording this. It goes out to the web forever. You want allowing questions during your talk, or would you like to get to it?
I'd say I'll pause at specific moments for questions.
Okay.
Because there is a lot of content, and I want to make sure that we have a chance at getting through it.
And our next TWED is going to be Enrique in 3 weeks on the 22nd. So without further ado, take it away to Abraham. Thank you.
Awesome. Welcome everybody to the TWED talk. It is titled Towards Fluid AI Conversation with Natural Turn Taking, Full Duplex Modeling with Audio Codec LMs. And hopefully by the end of this talk, you'll have some idea what that means. I'm still figuring out what it means because it's the topic of my dissertation. Okay, so we'll talk about, we'll introduce the topic, we'll talk about how turn taking works in real human to human dialogue. Then we'll go a little background on spoken dialogue agents, and then how we'll get into the technicalities of how we might want to go about building a full duplex dialogue agent that is human-like, codec language modeling. So if you have two people who are talking to each other, you have a lot of rich interaction potential that beyond just the content of what they're saying. You have laughter, you have pausing, specific coordination of turn taking, interruptions, backchannels, acknowledgements, like yeah. You have filled pauses such as or These things, like if you ever talk to ChatGPT, you notice that in their audio mode, all of that stuff is completely absent. It's just like talking to a very, like a studio quality robot. So, yeah, all of these things, I call them paralinguistics. Well, as other people call them that as well. But the non-contentful content of what you're saying actually does hold a lot of content. It holds signaling and coordination information that lets a speaker know whether or not you follow them, or whether you're engaged with them, or whether you're listening to them, or whether you need to go back and clarify something, etc. So there have been lots of history of this stuff being studied, both in cognitive science and in computer science. In specifically cognitive science, there is a field called communication, conversational analysis, or CA, not communications. Conversational analysis involves analyzing transcripts of spoken conversations and annotating at what points in those conversations these paralinguistic phenomena occur, and then being able to study frequency, statistics, and other things to get a sense for how humans communicate. So traditionally, spoken dialogue systems, like ChatGPT, are implemented as cascaded models. So you have some speech recognition system, you might have an LLM in the middle that's acting as a chatbot, and then you have a text-to-speech system that is transcribing the responses into speech. But these models fail to produce all of those paralinguistic phenomena because, and thus they're not fluid and lifelike. It's like talking to a studio quality robot. So why is this? And one reason is because they implement rigid half-duplex turn taking. Half-duplex specifically means that only one person can talk at a time. There isn't a parallel bidirectional communication, which would be full duplex. And also there's no modeling of the prosodic and paralinguistic features that we just talked about, no modeling of laughter and of rate and pitch variation and filled pauses and things like that that you might expect in a normal conversation. And also, cascaded systems suffer from an inescapable issue, which is error propagation. So if there is an error that is made by the speech recognition system, that will propagate to the LLM chatbot, which has never actually heard the audio. It's just received some text, is treated as gospel from the speech recognition system. And that same thing, the text-to-speech, receives some text from the chatbot, treats that as gospel, has no idea whether or not it is actually the result of some kind of an error. So the further back in the pipeline that the error happens, the more can go wrong later on. So like if you say, what's going on? And it hears watch going on, and it's, oh, is that a show? And be like, well, that doesn't sound coherent at all, given what I asked. So why not handle all three of these functions in a unified model, and specifically a full duplex autoregressive model? And that's what we're going to explore today in this talk. And again, full duplex means that each party in the conversation has the ability to speak simultaneously. There is a true bidirectional communication that is open at all times. So both parties have to figure out when is the appropriate time to speak and when is the appropriate time to yield. Otherwise, they'll just talk over each other. So I'm going to go through this section a little bit fast. This is the turn taking in human dialogue. It's just a little bit of a background on what's been studied in the cognitive science literature on this. So there was a seminal paper by Sachs, Shegloff, and Jefferson in 1974, and other follow-on papers that discuss, basically create a systematics for analyzing human dialogue. And there are essentially units that can be taken, such as the turn constructional unit, interpausal unit, and transition relevant place, which determine how you can compose a duplex human conversation. So for example, a turn constructional unit is going to be potentially multiple chunks of audio separated by a pause, whereas an interpausal unit is what you can use to construct your turn. Multiple things that you say sequentially with maybe some pause in the middle. Then you have backchannel acknowledgements, which are small interruptions like okay or uh-huh, which are not meant to take the floor from the other speaker, but are there to help guide the conversation by telling the other speaker that you're following what they have to say. And again, you have all of these different possible phenomena. You have positive and negative offsets, so either a gap, a pause, or an overlap, meaning people speaking over each other. Filled pauses, such as and you know, which are specifically there in conversation to signal to the other speaker that you're not done speaking. Don't start talking yet. I just have to think about it. Back channels, like I was just saying, they help tell the other speaker that you're following them, or maybe not. And then you have other prosodic clues, such as intensity of the speech, speed of the speech, emphasis on words, tone, drawn out syllables, etc. You have laughter, you have singing, grunting, squealing, humming, singing, all of these things that can occur within human speech. And you also have things like choral speech, speaking in chorus, such as, ever heard two people greeting each other at the same time? Hi, how are you? While the other person's also saying, hi, how are you at the same time. So cascaded half-duplex spoken dialogue systems, then check. Don't do any of these things well at all. So this is a transcript from an actual human dialogue shared on TalkBank, which is a repository of transcribed phone calls. We'll see if we can play one of these. Make me log in. Okay, give me a second.
Okay, set up the music.
What?
Set up the music.
Why don't you go first?
I guess I'd have to raise my computer volume temporarily. Okay. Doesn't work. If I wanted to share audio to be played on,
Oh, I don't know how that would
we
work.
probably want to increase the volume of the audio from the TV, right? Is there a remote somewhere?
Yeah, but it's coming from me. If
Share.
can I hit your share audio through?
It's doing that, but we don't hear it.
Oh, I know what to do. Well,
I don't know. I just been going crazy lately. Like, sometimes it seems like every Sunday is like a real like dullard for me. Not like like it's like a big like loser day for me. Like I had this big paper to write.
Oh, that's what I'm doing right now.
And I left it to the last minute. Like I was in class when we had to choose our poet. On like last Wednesday, and my professor goes, "So who are you choosing?" And I go, "Ezra Pound." Like right off the bat, you know what I mean? It wasn't even on the list. I just wanted to like Ezra Pound is like pretty big. It's like a big thing, you know what I mean? So my professor was all like winking and smiling at me. He was so pleased. So like yesterday, I go to the bookstore and I buy Ezra Pound poetry. And I come home and I'm like sitting in the bathtub trying to read this shit. And I go, what? Like I've never encountered poetry like that before. It was like her span down the last, and then Icumen, Greek statement.
Not
Like
me.
it was
This is
just like
not. So I think that dialogue up there is you.
Okay. Oh, that doesn't do anything if I click on it.
I don't know. I think you just gotta.
Okay.
some sort of
So I've unmuted
dissertation
myself.
or something.
Right?
It wasn't like poetry for the masses at all. So then today I had to go to Borders, and like, you know, I couldn't buy like 3 of Sonia Sanchez's books. You know what I mean? That's like $40.
Right?
So I just sat there for like 3 hours and copied down 30 poems. And then I like walk home and I'm like all depressed and I'm like writing.
So this is
poetry,
coming out of my
like
speakers.
all this stuff like nose grows.
I don't know if there's
like,
a.
all this shit, just like all this sad, depressing stuff in my life. And I think I should write a poem. I should write a poem. And I was walking.
I did.
At home like all depressed and sad and blue, and then I just started typing all the poems.
And now you have this like orange color padding on top of your like screenshot, right? It won't show in here.
Yes.
Okay, there should be 3 buttons horizontal. Go there,
Mhm.
and there should be share computer audio.
That's already checked.
Oh,
I don't know.
Just keep going.
All right. I'm sorry, guys.
You can't play audio just from your laptop, can you?
I
But he was
I
doing.
can, but you guys aren't going to hear it unless you
It's really faint.
over here.
Just keep going.
All right. Well, we tried. So I'll go back to the slides. So humans use turn-taking cues beyond timing of interpausal units to predict when or when not to take their turns. They use those other cues include the content of the utterance, such as syntactic completeness, whether or not you actually finished what you had to say, prosody, whether you're holding a pitch or whether it's increasing or decreasing, and the average gap length that occurs in natural human dialogue has been measured in specific corpora to be about 200 milliseconds. So about 200 milliseconds on average will go by between when one person stops speaking and the next person starts. And this indicates that people have the ability to predict when somebody's turn will end and when they would be able to come in and start responding, and that they can prepare part of that response in advance. Spoken dialogue systems don't really work this way. They don't use those type of acoustic cues, and they don't predict turn-taking events in advance. Rather, they typically use a voice activity detector to predict when the speech has stopped, and then start queuing up a response at that point using whatever LLM component is part of the system. If the dialogue system was able to create an overlap, it might want to support these types of overlaps, which are measured or which are observed in human. One is called competitive overlap, which is where maybe one person is starting to speak before the other person is done, and then maybe one of them will stop speaking or continue speaking to signal, hey, I'm not ready for you to speak yet. And it might sound like an interruption. Then there's cooperative overlap, such as backchannels, which we discussed, things like and conditional access overlaps, which is like a sentence completion. If you have somebody who is able to predict what you're going to say, and then they come in and then they complete your sentence for you, or how that happened. Terminal overlap happens. Oops, sorry. Actually, I'm not sure. I forget exactly what terminal overlap is. I'm thinking of a different word for it. This is on a slide which I don't remember what it means. So moving on to computational models of turn taking, with the goal of improving the fluidity of spoken dialogue systems. So work has been done in this area for many, many years, going all the way back to 2000 or the early 2000s. The neural models of turn taking have been explored since about 2009. Well, if there's anybody who actually knows this field in the room, they're going to be saying, what are you talking about? Neural models have been explored a lot earlier than this, but the first operationalized turn-taking model that was basically an attempt to create a duplex dialogue system with it was in 2009. This was the numbers system, which basically just accepted a person dictating a stream of numbers, and then it would respond to confirm whether or not it accurately heard what the stream of numbers is, and could interrupt you if it felt like it had not heard numbers correctly for a confirmation. You have Sconsi in 2017 presented a predictive model of turn taking. So given a stream of audio, it could predict at what points a turn switch would happen, and it used a RSTM for that. Similarly, Meyer, Hugh, and Schlangen in 2017 built a neural model that used both acoustic and lexical features, so combination of text and audio. And there was similar work in 2019 where there was a probabilistic model of when a transition relevant place would happen. Transition relevant place is not specifically when a turn happens, but when a turn could happen. So it's predicting all of the places where a turn switch would be reasonable in the dialogue. And here are some transcript-based models that use just text to try to do the same thing. Essentially, if you can transcribe the spoken dialogue, then then you can potentially guess where a turn might be taken or where a relevant place might be, even without the audio. So now how would we operationalize this as a spoken dialogue agent? So this section just goes into what spoken dialogue agents are and how they're traditionally implemented. So if you ever had one of these, it's an Amazon Echo, right? It is like most other dialogue systems. Well, I don't think people really use them anymore, or at least I've never seen them recently, but I think they still exist. Like most dialogue systems, an Echo is a cascaded dialogue system. It has a speech recognition component, an LLM or some kind of natural language NLP processor in the middle, and a text-to-speech system. It is non-incremental, which means that all of the steps of understanding what was said and speaking and choosing what to say next is happening in series. In actual human conversation and in a duplex, we would want this to happen in parallel. So you could be listening to what's being said, understanding what's being said, getting ready to respond, all while all at the same time, essentially. So the number system from Sconsi and Schlongen was the first system to do this successfully, even though the domain of the conversation was just streams of spoken numbers rather than general conversation. Since we're having trouble with audio, I'm going to skip this. We'll come back and try to play some of the later audio if we can, but I'm going to skip this. This one. So incremental speech processing, which is that model where, like in humans and in duplex dialogue systems, you have understanding and planning for response all happening at the same time. Turn taking is done continuously. You don't the other person's done speaking to decide whether you want to take your turn. You are constantly, every couple of milliseconds, predicting whether or not now might be a good time to butt in. So the question then is, well, why can't we handle all of these functions in one autoregressive model that will retain both the acoustic and semantic context at all stages? And can that model also be a continuous model of turn taking as well? So that brings us to codec language models, which is the tools that we would use to implement such a system. So a quick background on language modeling, which I think none of you in this room need, but it's here. Tokens are generated autoregressively after being tokenized. So you have text comes in. Text is broken into subword units called tokens, and they are converted into embedding indices, which are then looked up in an embedding matrix. The embedding matrix it returns a vector for each token, which represents its sort of semantic position within the space of possible tokens. And that sequence of tokens is then fed into the transformer, and the transformer is able to use attention to contextualize each token and do things like solve coreference and combine, track where we are in a conversation, do retrieval from context and things like that. So the immediate question is, when you build an audio language model that's going to do duplex conversation modeling, what are the tokens going to be? You might think that an acoustic token or an audio token should represent a unit of a sound rather than a unit of a language, like text, right? So for this, we would turn to audio codecs. And you might recognize MP3, AAC, FLAC, WAVE, if you've ever streamed audio to your phone. These formats are actually audio codecs. They take raw audio waveforms and convert them into digital signals or discretized sequences of numbers, like this. You have an encoder. It takes the audio in, it discretizes it to a form that can be efficiently transmitted over a network. And then the other side, there's a decoder, which converts it back into reconstructed waveform. So these discretized units of audio can be our tokens. And MP3s and AAC is actually a little bit too, it has too high of a frame rate for us because neural networks have limited context windows. So we could turn to a more efficient form of compression, which is implemented as a neural audio codec. And we can take audio and compress it into about 1.5 to 24 kilobits per second, whereas MP3 is typically 96 to 320 kilobits per second. So how do these neural audio codecs work? Basically, the codec has an encoder and a decoder. It's able to take the sampled audio and output a sequence of embedding vectors that represent the unit of sound. So at t equals 1, t equals 2, all the way up to t equals n, you have an embedding vector that represents in a space of possible sounds. This sound sounds similar to that sound, so we're going to embed them close together. So this is great, but this is even more information than potentially the raw audio waveform, because the raw audio waveform is just a single dimensional stream of data at a very high frequency, whereas these vectors can potentially be hundreds of their dimensionality could be in the hundreds. So we use vector quantization to convert these vectors into integers, kind of the same way you do with vector quantization. Will basically take the it'll essentially, you can think of it like k-means. It segments the space up into of clusters or regions, and the centroid of each of those regions represents that entire region. So you have a centroid vector that represents the typical sound that would occur in that region of the space. So you can then convert all of these units of sound vectors into, basically k-means. You can convert these unit of sound vectors into indices, which would be the indices of the code of these centroid vectors in a lookup table. We call that a code book, and we call the individual vectors code words. So this is basically the same thing as we're doing for text, except we use different terminology for it. We use embeddings and tokens rather than code books and code words. But it's the same thing. We now have a stream of integers, and each integer represents a small unit of audio. The analogy, tokens instead of code words, embeddings instead of code words, tokens instead of code word indices. When we have a sequence of these code words or audio tokens, we can then feed them back into a decoder, and the decoder can reconstruct a lossy version of what was originally encoded. How lossy it is depends on the implementation. There's a whole section on something called residual vector quantization, which I actually omitted from this presentation because it's for the sake of time, but there are methods that can be used to reduce that loss. So we have powerful neural audio codecs now that have cropped up in the last couple of years. These are some of the earlier ones, and Codec, Soundstream, and Fun Codec. But at this point, I have a folder on Zotero that keeps track of all of these things. It's probably tripled in size over the last year. So we have lots of audio codecs, which are basically autoencoders with a discrete bottleneck that can convert audio to and from sequences of discrete tokens. So given that, all we have to do is make an LLM, except the LLM doesn't take in text tokens, it takes in these audio tokens. And we encode the input and decode the output, and then we're done. That's it. So some examples of codec language models include Audio LM, which is a very early one attempt at this from Google. This was done as a 3-stage language model, where each stage would input and output tokens which represented larger and larger units of audio. So the first stage had the largest, they call them semantic tokens. These are large chunks of audio, and the idea is that the tokens are supposed to represent the meaning of what's being said. Whereas you have then acoustic tokens, which are very granular chunks of audio, and they represent the sound properties, the acoustic properties, pitch, tone, intensity, all of that. So there's a separation between semantics and acoustics here. Audio LM was a very significant step in this direction because it was the first to really try this and do it successfully. And it actually worked both for speech and for music. And there are some examples here of what those outputs sounded like. Let's see if we can get this to play. So I'm going to stop sharing. I'm going to share again, maybe directly from the Google Chrome window. Maybe that'll do it.
This transit, spring, and lighting up are beautiful.
I don't know what,
Do you have, is there that remote? Maybe the remote itself is muted.
look like, I really don't know. I mean, you're
A
not
glamour
connected to
beguiling
that.
our senses.
But
This transit,
my audio
spring,
should
and
be
lighting
being
up are
transmitted to your
beautiful.
machine, and your
A
machine should be
glamour
playing
beguiling our senses.
over that, right?
Yeah. Try it once more.
This transit, spring, and lighting up our dreams by its brilliancy and beauty. A power which, if we shut our eyes to it, will not shut.
All right. I'll play it from my laptop. I guess you guys do the best you can to hear it. I'm sorry. I'm going to, or can you mute that so it doesn't echo?
Yeah, which one?
That one.
This transit, spring, and lighting up are beautiful. A glamour beguiling our senses. This transit, spring, and lighting up are beautiful.
Well, I think the muting the WebEx doesn't affect audio sharing. It just affects my voice input, but whatever.
Yeah, that's for people remote. Yes, for the people remote, that makes sense.
Yeah, I was saying that because the audio is coming from the browser, not from the microphone, it probably, whatever. I'll do it anyway, just in case. So, so that's the prompt, and then the continuation sounds like this.
This transit, spring,
After
and lighting up our dreams by its brilliancy and beauty. A power which, if we shut our eyes to it, will not shut.
So it was able to generate speech with the same acoustic properties, although probably not very coherent, but still reasonably well. And then it also was able to do the same thing with music. So piano music. Here is the prompt. And then here is the continuation. So this was, I guess, now I should remute myself.
So you can probably just continue because it's picking, the recording's picking up you.
Okay, but then we won't be able to hear anybody over the.
No, it's different.
Okay.
They wouldn't be able to hear people in the room. It's you guys.
All right, so we'll just leave it this way, I guess. So coming back to the slides. So yes, this was, Audio LM was a big step in the right direction towards being able to do stuff like this. There was DGSLM, or which stood for spoken dialogue language model, and took inspiration from Audio LM, except it only used a single stage of codes. It didn't separate semantic and acoustic codes at all. But what it did is it had two different decoder heads, or two different decoder stacks altogether. They had one for two different speakers that could be potentially talking to each other. And we'll get that. That's a very important detail, which we'll talk about pretty soon, because that's critical for duplex language modeling. And I'll play some samples from that. So this was, again, a prompt and continuation type thing. So
Hi.
Hi, my name is Dee. How are you? What's your
Good.
name?
So after the ding, it's going to play the model's continuation of that conversation.
Hi.
Hi, my name is Dee. How are you? What's
Good.
your name?
My name is Debbie.
Debbie. Where are you calling from?
North Carolina, and it's about the age before or right up. Yeah, people on a vigilantly care stand up.
Oh, Costa, Wabby.
Yeah,
Yes.
but she has at least big town here
Yeah.
from the theater one by was. You can't imagine.
Boy. Oh, Isolone, I know. And they are Peace Boys. They're not learning to. Also, a Peace Boys, also they get the best on the theater. And
wow.
it's about to change it.
So that sounds very natural, but unfortunately the words are not actually real, right?
It was Southern, so I just, I didn't understand it.
So, and this is a very important point, which we'll talk about in a second. So this model had two concurrent channels, one per speaker, and each channel, the audio codes for each channel went through a separate decoder stack. They called it a dual tower LLM that had a cross attention between both stacks so that at each time step, each speaker could attend to what the other speaker had said. And it used k-means quantizer on a Hubert encoder. That's just what they used for their codec. And for decoding, they actually used a separate, it wasn't like a single autoencoder, but rather they used a separate model for decoding. We also had Volley, which was a text-to-speech system from, was it Microsoft, I think, right? Yeah. And this was a language model which took phonemes and an audio enrollment sample. Basically, you could do voice cloning with it. This was one of the first models that could do effective voice cloning. Now, you go to 11 Labs or you go to one of many different services and you can do very, very well effective voice cloning, but this was the beginning of it. But all of this is the same paradigm. You have a language model, you're feeding in the sequences of audio tokens, and then you are generating continuations of that. Here's another more recent one called, well, they didn't name it this, but Hugging Face implemented this, re-implemented it and called it Parler TTS. But anyway, this paper introduced a text-to-speech system where you could feed in not only a text, but also a prompt of what you would want the speaker to sound like. So if you want the speaker to sound like they're a cowboy, you would say, speak like you're a cowboy. And then you would put in the transcript and it would give you a codec decoding of that. So we can listen to that. Maybe we can listen to it. I guess we can't listen to it. All right.
It's not a government server, is it? Consider shut down.
No. So here's a question. And I guess we probably should have heard the samples from that, but to understand the question, which is why is AudioLM and DGSLM unable to produce coherent speech while the text-to-speech models could? If you would have heard, if that page would have loaded, you would have seen that the text-to-speech system was very coherent. It was able to faithfully translate the text into speech. And the reason for this is that these acoustic unit embeddings, they encode some information not only about what's being said, but also how it's being said, what the acoustic properties are. For example, the word dog spoken in rapid speech with a rising pitch, a female speaker with a Southern American accent. All of that information is inside of this acoustic unit embedding. You could have many or potentially infinite embeddings for the same word. A dog spoken slowly with a level pitch, or with a falling pitch by a male speaker with a Scottish accent, right? So same content, but infinitely many possible embeddings. So if you have a speech context and you have the set of possible semantic continuations, so the words that might come next, and you have the set of possible acoustic settings, so you can think of it like there's a Cartesian product between S and A here. So for AudioLM and DGSLM, you have the space of possible continuations are in the Cartesian product of S and A. You have every possible word times every possible speaker times every possible acoustic background position. So in text-to-speech models like Volley and the other one that I tried to show, the possible continuations are only in the space of possible acoustic settings, because the semantic conditioning from text constrains the space S. So it's a much smaller possible output space of predictions, and that's why the models are able to learn coherent speech rather than just replicating the acoustics of it. So the interesting thing here is that AudioLM and DGSLM are full language models. They're actually trying to learn to reproduce speech from scratch by jointly encoding the semantics and the acoustics in audio tokens. The text-to-speech ones, they're doing a much simpler modality transfer task. So if we want the simplicity of the modality transfer task to work with full audio language modeling, the solution would be interleaved audio text codec language models. For example, this one, Speech GPT, they take a interleaved sequence of text and audio and as input, and they output an interleaved sequence of text and audio. GPT-4o also does something similar to this. We don't know exactly, they didn't release the technical specs of this, but GPT-4o natively generates audio and text from the same model, and its context can contain both audio and text, and it is able to respond within an average of 320 milliseconds because it does everything in a unified way. Here is a list, if you're interested. Yeah, hopefully only the people on my committee are interested. Of all of the interleaved audio text models that people have done recently, if you look at the years, I mean, it starts in 2023 and then explodes in 2024. I haven't updated this for 2025. It's probably 3 times as long by now. So interleaved audio text models have caught on, and it's a very common pattern in audio language models. So this brings us to the problem we're trying to solve, which is full duplex spoken dialogue systems. So a codec language model would be full duplex if it contains a mechanism for parallel token streams. Remember DGSLM, we'll get to that in a second. But on the left, you have a half duplex codec language model where user speech comes in over a codec, is converted to audio tokens. A voice activity detector will detect the end of the speech and signal the end of the turn, which could be signaled in an end of turn token. The end of turn token then conditions the model to start generating speech, which it outputs as its response. And this is very fixed. I go, end turn, you go, end turn. I go, you turn, end turn, you go, end turn. Whereas full duplex doesn't have any of that nonsense. It just has a parallel stream of input and output codes. At every time step, you have both what's being said on 2 channels by 2 speakers being both input and predicted. And the speech that we want to continue would be the agent's speech, which is passed on to the next time step, and the speech that's coming in from a microphone would be substituted in from the codec. Of course, you could do this with both streams and generate like a self-play type of thing, but at inference time, we would typically bring in one stream from a microphone and have the model generate the other stream. So there's no voice activity detector, no concept of an end of turn because we don't have any clear turn boundaries. And we have continuous parallel input and output, which lends itself well to the continuous model of speech processing, which I spoke about earlier. So recall DGSLM, right? They're essentially doing the same thing, except rather than having one decoder stack handling both streams, they have 2 decoder stacks, 1 per stream, with a cross attention between them. So it was it's the same thing, just with a different skin on it. So more recently, there's been a couple of attempts to do full duplex dialogue modeling. Some of them worked out pretty well, such as Moshi. Moshi came out of a lab called Qtai Labs, which is based out of France. They have a 2 model setup, one called the helium temporal transformer, which is basically modeling the first layer of a residual audio codec, and they have the temporal transformer, which is modeling all the other levels of the residual codec. So it reduces the number of time steps that the main model has to handle, essentially. And they use a dual stream system just like us, except each stream has multiple levels. That's what I was saying. Each level models the residuals of the one below it. So here, all of this is the agent's speech, and all of this is the user's speech, and each of the columns here represents a single time step of inference. See if we can hear some examples.
Save time creating content and generate a high quality.
Hi all, thank you for joining us. We're super proud to present you Moshi today. You can see its UI actually right now on the screen. So on the top right corner, you can see some delay. We'll tell you more about it later. And you can also see some text that will be printed by the model there. So it's a multimodal model, and Alex will tell you more about it later too. So let's dive straight into a demo.
Hello, how are you today?
Hello, can you tell me your name, please?
Hi, my name is Moshi. How can I help you today?
Hi, Moshi, can you tell me more about yourself?
Certainly. I was created by the non-profit research lab QTI, which focuses on using AI to tackle the main challenges of modern AI.
Okay, that sounds great. Do you know what open source is?
Yes, open source refers to the practice of sharing software source code free of charge.
What are the benefits of open source?
One of the main benefits is that it enables collaboration and allows individuals and organizations to contribute to the development of the software.
Okay, that sounds amazing. Now, my friend Edouard has a few questions for you too, if you don't mind.
So that's Moshi. There's also
in that demo right at the end, when he says that his colleague has some questions and she goes, of course.
Yep, that was a back channel, or actually, of course, could be both a back channel and also a response. I think in that case it was a back channel. So, so this is also another recent architecture for this called SyncLM. With SyncLM, you have decoding set up or segmented into chunks, where each chunk contains both audio from the user and audio from the agent. So it's more of like a flattened interleaving of speakers, but both but still modeling both streams simultaneously, because chunk N is going to have one from the user, one from the agent, and chunk N+1 is going to have one from the user, one from the agent. So over time, over hundreds of chunks, you'll essentially have a blended modeling of both streams. Here is a list of unified and full duplex spoken dialogue systems from prior literature. These have been popping up also like really quickly. A lot of them, most of them implement custom architectures to deal with dual stream modeling and multi-level codecs. Also, a lot of these are a lot of the sort of center of gravity for research in this area is actually in China right now. So the last 10 minutes we have, I'll talk about the my current research, which is essentially I'm trying to build a full duplex codec spoken dialogue system as well as the basis of my dissertation research. The data sets I'm using for this are necessarily split channel. So the Fisher corpus, the call home and call friend corpora, these are old data sets of recorded phone calls, except what's important is that each speaker is isolated on a specific channel, because you need each channel corresponds to each type of audio code. For example, the blue audio codes here are from channel 1, the gray ones are from channel 2. So if we don't have split channel audio, we can't train a model to do dual stream modeling. So what I'm doing here is basically taking a larger subset of mono audio to pre-train the model, or to domain adapt it, since I'm already starting with a pre-trained llama model. And then a small subset of split channel audio, about 2,000 hours to adapt it for duplex dialogue. And the architecture that I'm using is actually very similar to what I originally showed here, except instead of stacking the parallel channels, they're being interleaved in a flattened way, kind of like what sync-LM was doing. So you have one token from the user, one token from the agent, one token from the user, one token from the agent. Agent tokens are passed to the next time step. User tokens are provided from a microphone. That's it. So this allows the use of existing LLM architectures and optimized inference engines out of the box. Nothing custom here. We can use Llama 3.2 with Llama C++ immediately. Don't have to retrain it from scratch using, trillions of tokens of text and millions of hours of audio. Also, we're interleaving the text and the audio to provide semantic conditioning to solve that incoherence problem. So we'll have interleaved speakers with interleaved text that represents what the speakers are saying. So here you have one speaker says, yeah, the other speaker says, that's great. And in between them, you have the audio codes that represent those utterances. Where when B is speaking, A's codes will be mostly silent, with maybe some background noise. And when A is speaking, B's codes will be mostly silent, also with some background noise. But they could choose at any time to overlap or to do things like laughing together and things like that. So for a backbone, I'm using Llama 3.2, 1 or 3 billion parameters, not the instruction tune versions, because instruction tune models, they actually enforce a half-duplex turn-taking mode through their chat templates, which is an interesting choice of, or sort of like an assumption that's built into them that no conversations will ever be had in a duplex manner. And then the codec is called Magic Codec. It is a recent codec. It was released this year, and it basically takes 16 kilohertz audio and using a codebook of 131,000 possible tokens, it can encode that 16 kilohertz audio into 50 tokens per channel per second. So in my model, I have 100 tokens representing a single second of audio from both channels. So there's 5 training objectives. One is audio only, just predict the next token, audio token without text. And of course, if this was the only training objective, we would lose coherence, as we showed before. Text only, so that we don't forget how to model text, right? Audio first, so this predict the next response token given both the audio and the text, where the audio conditions the text. So audio comes first. This audio is then transcribed into this text utterance. This audio is then transcribed into this text utterance. You can think of it as a continuous speech recognition system. And then the text first direction predicts the next audio token given both the audio and the text, but now the text is conditioning the audio. So you have here, this text is conditioning this audio and this text is conditioning this audio. So it creates a text-to-speech system. And finally, the agent mode, which is what we use in real-time inference, combines those last two modes. So you have channel 1 uses text first, or text-to-speech, and channel 2 uses audio first, or speech recognition. So in a single stream, we have B's utterances are being transcribed from audio to text, and A's utterances are being transcribed from text to audio. And this is what an actual stream looks like. So we have here in blue, we have the header, which basically represents who are the speakers, and in a short enrollment of what the agent's voice should sound like. So it's like a style transfer for the agent's voice. And then you have starting in the black section, you have interleaved text and audio codes, where every other audio code belongs to either the user or the agent. And what you see here on the screen is just a Unicode rendering of the audio code, of the codes, because there's no meaning behind the Chinese characters or emojis here. There's just arbitrary Unicode rendering.
What does it represent?
It represents each code represents 20 milliseconds of audio from a single channel.
Is it audio code or is it embeddings?
These are tokens and they correspond to embeddings. So finally, we get to the examples. So the details of the inference, I'm using Llama C++ as my engine. It's really nice. It's able to run at like almost 300 tokens per second on an A100, which is great. So that's about 2 times, with all said and done, it runs about two times real time on a single A100. It runs using the agent mode with a 6-second enrolled voice cloning sample, and it can process audio in 100 millisecond chunks, so essentially 5 forward passes per second, and thus can react to user input with less than 200 millisecond latency, which is, if you remember from the very beginning of the talk, is even less than the average latency found in human dialogue. So here are some generated conversations and a real-time interactive conversation to listen to what the model sounds like. So the generated conversation, the model generates both sides in audio in text first mode, and the interactive one uses agent mode.
Hello.
Hi.
Hi, this is Greg.
Hi, this is Mike.
Hi, Mike. How are you?
Pretty good.
Cool. So I guess we're supposed to talk about issues with the Middle East?
Yeah.
Okay. Well, I'll let you get a word in first.
Sure.
Just all the model. I didn't condition.
I think it's a tough situation. I don't know. How do you
It
feel
is
about
a
it?
tough situation.
Yeah, I think it is too for me.
I think that the U.S. needs to take a much more active role in the peace process than we've been doing lately.
Yeah.
If we could, if we get Israelis and Palestinians.
Notice the yes that were going in there. Those are our back channels. So the other guy isn't interrupting. He's just saying, yeah, I'm following.
To kind of lower the heat a little bit. I think
Yeah.
that's the only thing that would help the situation.
So that's what do you think it's the only thing that would help it? The peace. How do you think the peace process would work?
Well, I think.
So one of the topics in that Fisher data set was actually the Middle East conflict. And this was back in 2004. So we know that that's been going on for a while. Here's another generated sample.
I'm David.
Hi, I'm Bob.
How you doing?
Not bad. How about you?
Good. Where you calling from?
New Jersey.
New Jersey. Okay, I'm in San Francisco.
Oh, well.
So what are we supposed to talk about?
About, do you exercise regularly?
Yeah. Well, I don't know. I just signed up for those things. I've had their start.
Yeah, this is my first call.
Oh, really?
Hey,
It's my third. I think
Oh.
that I don't do it on a regular basis. I know it depends where I'm at. I'm in school.
Oh, yeah.
There's no
Yeah.
prompt.
So like.
It's just
I'm
allowed to
kinda
talk about
active,
anything.
but not like working out or anything like that. So.
Oh, yeah.
It kind of depends on
It
where I
sounds like
am
they're
and what I'm
keeping
doing at any given time.
exercising.
Oh, sure. Sure.
The
So
Fisher
what are
data
you
set-
into? Any kind of sports in particular, or are you,
No, none really.
okay, just the weightlifting and so
Yeah,
forth?
that stuff like that.
Yeah, so in the Fisher corpus, participants, when they collected that data, participants were given one of 10 topics to talk about, and then they had to talk about that for 10 minutes. So here, the model that basically decides which one it's going to go with, and then it just goes with it. I don't tell it, hey, go talk about the Middle East. It just says, well, that sounds good. Next token prediction, high probability, next token, let's run with it. And it runs with it. So, and here is an interactive one where I'm actually interacting with the model.
Hello?
Hello, how are you?
Hi, doing well. How are you?
Good. This is David.
David, this is Sean. How are you, David?
Hi, good. Where are you from?
Houston.
Nice. I'm from upstate New York.
Oh, really? My sister and brother-in-law just moved up Houston with their daughter.
Oh, okay.
Where
Cool.
are you from?
Oh, upstate New York.
Oh, that's good. Okay.
Yeah. So, what do you do for a living?
I do restaurant management.
Oh, cool. You run a restaurant, or do you own one? Or?
Yeah, it's I'm managing restaurants, but it's like I own one day, worked for it, and I do like inventory things like just hand washing and stuff all the time. And they sit
I hope you guys can hear it.
around with the
Kind of quiet.
So you're doing stuff like whatever needs to be done around the shop, and that kind of stuff.
Yeah, that's a ton of stuff. I definitely need to though. I need to.
It's just pure generated based on what you're. So you essentially are the prompts.
Yeah. in that case, I'm a live prompt. Basically, my audio codes are going in, and its audio codes are being generated every 100 milliseconds in an interleaved form.
So what was her name? Eliza? Eliza?
Eliza?
You know Eliza?
Like the original?
Synthetic psychologist from like 1963.
Yeah, so we'll end, I know we're a little bit over time, but basically there's a question of how to evaluate this. And there is an existing paradigm for evaluation of conversations that's, I know LLM as a judge is used a lot now, but in 2019, there was something called a Q-eval, which would give two different conversations between two systems to a human judge, and then ask a question such as, which speaker would you prefer to speak to it for a long conversation, where speaker A came from system A and speaker B came from system B. So we can do something similar with recorded conversations and basically ask for A to B comparisons between the speakers in the recorded conversations, and then compute a win rate or an ELO score or something like that between different systems, including one system which is actually two humans talking over the phone. We can also give surveys which ask participants to rate A or B essentially on a bunch of different axes, such as who is most coordinated overall, which conversation has acknowledgements used most effectively, which has the least inappropriate interruptions, et cetera, et cetera. So human judges can listen and be like, hey, that sounds awkward, or hey, this actually sounds really good, and then vote for system A or system B accordingly. And if the duplex system can win against human participants reasonably high number of times, then that would validate the approach. So the general evaluation will be listen to a 1-minute conversation, either self-play or human-human, fill out the post-survey, and compute the win rate. And I'll skip that. So to conclude, human speech is much richer, carries much more information than traditional text chatbot interactions, and future spoken dialogue systems can be a lot more fluid and human-like if they embrace incremental full duplex approaches. And that's it.
Mute your WebEx and I'm going to. Wow.
Okay. Should be good now.
So, yeah, the question I had was that somewhere you were. So where is it in terms of encoding semantics into the affectations? So in that last example you had where you're interacting with the generator, is there any actual semantics encoded? Like, and heard that what did you call it originally? Like the affectations, her tonality and all that kind of stuff, her pauses, is there?
Yeah, all of that's encoded in the audio codes themselves. Content of the speech is conditioned by the text. So like if let's say the text is, oh, that's great, right? You can say, oh, that's great, or oh, that's great, right? So whether or not she does A or B is conditioned by the context, so acoustic context, but whether or not in the prior couple seconds or maybe minutes of audio, she is speaking in general with a higher or lower tone. And then you have the ability to use the semantic information actually to trigger a change in the tone. So the acoustics are preserved over time, and the model can also vary them according to what's being said. But the information that models the acoustics is purely in the embeddings of the audio codes. There's no separate features or models that are there to encode that.
Okay, that's perfect. So in terms of languages, their meaning is based on like the tonality. Where there's some languages in the world where
like the tonal languages.
Yeah, exactly.
Mandarin, I think.
Yes, exactly.
Yeah, I mean, systems like this would probably do better than cascaded systems in those particular instances. Although maybe not. I mean, as long as a text-to-speech system has a way to represent what the tone should be, then it can probably do it as well. But I mean, if there's a language where information is carried forward in timing, then something like this would have an absolute advantage. Yes.
Can it handle sarcasm? like those types of where the text of what you say, the words themselves, like cannot be removed from the tone of which you are saying them to actually get the meaning. Like, is that still a limit for these types of systems, or have you found that they can actually handle it well?
I mean, if there's lots of sarcasm in the training data, sure.
Fair point. Fair point.
Have you tried? I haven't tried. This type of data is hard to get. The split channel. Jade, go ahead.
Oh yeah, I was actually just going to ask about that. Like the trade-off between, I know obviously you didn't literally start from scratch since you said that you started from some pre-trained model as a base, but obviously most data that's available is text data, right? And obviously the conversations you were having with it were much less coherent than, what we can see with frontier LLMs, right, today. So I guess, how do you see this evolving? Is there perhaps like a way that it can go back and learn from some of the rich text-based model or pure LLMs to enhance it further?
So there's two things. One is that I'm using a 1 billion parameter model.
Okay.
So if you remember how coherent GPT-2 was, that's basically what I'm working with.
Okay.
If I had the money to scale this up, then I imagine that the technique itself is not the bottleneck. It's just the money to scale it up, to be able to have the GPUs to train, 7, 13 to 30 to 70 billion parameter models. Frontier models are hundreds of billions of parameters. So of course they can model lots of long context coherently. The other thing is the data that's used to train this models has to be split channel, whereas frontier text-to-speech systems can just ingest millions of hours of mono audio. So one way to potentially mitigate that is to first pre-train something on millions of hours of audio and then fine-tune it on a very small subset of stereo audio, which is what Moshi did. But pre-training anything on millions of hours of audio also requires lots of money. So hand me your money, I will make it happen.
I was mainly wondering about the trade-off. Like, is there enough split channel data to train a frontier model if you did have all of that money, which it sounds like there's ways of getting around it.
There really isn't. So what it would have to do is scale up the pre-training, train on a lot of mono audio so that it gets that interleaved, text to mono thing really, really, really well. And then fine tune on, maybe, 10,000 hours. I think I'm aware of maybe 30,000 hours total of possible split channel audio that's out there. You get it from the UPenn LDC, and you have to pay a lot of money to license it. But I've applied for scholarships to try to get that for free. But I was able to get Fisher. Now I'm looking to get Switchboard and several other corpora. But assuming you can get that data, you would want to pre-train on millions of hours of transcribed mono audio, and fine-tune on about 10,000 hours of duplex speech. And you should get something that sounds like a frontier model. Now, I'm working on a co-op right now for a company that expects me to put something like this into production and expects it to compete with 11 labs. So what do? I turn it into what I call a hybrid cascaded system, where basically the duplex model is sitting there just acting as a turn-taking coordinator, but the speech recognition, LLM, and text-to-speech is coming from frontier models. And getting all of that to run in real time is an engineering challenge, but I'd say I'm like 80% of the way there. So, yeah, good question. if anybody out there has a couple hundred H100s that might.
That's a line around.
Also, RL probably can help here too. There's been a lot of work on using RL to preference tune language models. RL would be able to potentially help guide what types of interactions are awkward versus not, if we had a model that could detect awkward interactions. So RLHF for something like this would be the human preference being rating which interactions sound the most natural, and then ranking outputs from such a system and then doing RLHF to preference tune it. So that could potentially be another path forward, except that won't increase audio quality or response coherence, but rather it would increase the accuracy of turn taking and lap management. Sasha, yeah.
Yeah. I have several questions. Start with the speaker consistency. Like when you have a character, either you interact with somebody or they interact with each other. You said it's a single LLM that's responsible for all of them, like generating various tones. Like there's this certain consistency in gender, tone, and attitude, right? As you speak. So one can, this is sort of as a character trait. You generate a personality, not only a speaker, because without a specific consistency of some parameters, you would shift from male to female voice, from ethnicity, from Russian to Spanish accents, right? But it doesn't do that. It keeps them consistent. So do you have any say as to how the model generates them, A? And B, is there any way of externalizing these parameters? Not externalize, but make them explicit.
So how to control the personality of the agent?
Yeah.
So if we're using an external LLM integration, like I was saying in my answer to Jade, then you could just prompt it.
But in
this case, if you're not using an external LLM integration, then you have no control over that. A future version of the model will allow some instructions or some personality trait descriptions to go in the header, and that's how you would control it. But
I would be very interested if you would be able to generate some sort of parameter set that you could set the personality. I think I could connect it to a cognitive architecture. Like this is where you can actually generate a choleric, a quiet person, somebody who is anxious, really personalities that you can interact with. And it seems like the model is doing it implicitly, where if you talk, for example, to the restaurant manager, it was a specific type of personality that you feel like you've seen before, right? It's not a very generic one. No, it was a specific type, like, you wouldn't believe that she's a restaurant manager because she was kind of lax and indecisive. And if you're a restaurant manager and you're like that, you're going to probably get fired. So, but there are, it seems to me like there are personalities and they're consistent there.
Yeah, right now, decision on personality is all left to the latent space of the model, but I mean, we can use ChatGPT or frontier model to annotate what the personalities of these speakers are based on their text transcripts and put personality labels or descriptions in the header of this model during training. That way it can provide a method for users to say what type of speaker that they're really looking for. So there's a path forward to that, just I haven't done it yet.
Oh, that's interesting. So, okay, there's also the questions, how would you annotate? Yes, because you would need to assess the personalities of the previous audio recordings in order for the LLM to learn them.
Right.
Yeah, that's also cool. I think Tomek wrote something in chat.
Oh, yeah. Could this approach scale up to multi-party conversations like meetings or parties? Yes, it could, as long as we have sufficient.
Yeah, you just read it.
Oh, yes. As long as we have sufficient data that represents the multi-party audio, the challenge there is that it would have to be, rather than speaker A on channel 1 and speaker B on channel 2, it would have to be speaker A on channel 1 and all other speakers on channel 2. So the agent is speaker A, and it has to choose who to respond to, but all other speakers are coming in on the same channel. And in multi-party audio data sets that we have now, like the ISL meeting corpus, for example, it's mono-channel audio. So we would need a method to split basically all of those speakers out onto their own channels and then combine them in such a way that each speaker is isolated on its own channel while the others are combined. That way we can generate the right type of training data. So having a high quality speaker separation model would go a long way in enabling that use case. And right now, there are only a handful of speaker separation models that are any good, and most of them are proprietary and offered as a service for money. So
yeah, but that's that cocktail party problem, right? We need to isolate who is talking to who, that kind of thing. But isn't there already work prevalent in the signal processing field that already does that to some extent? Yeah.
Saying that there are speaker separation and speaker detection models that do just that and are available. Not a lot of good open source options, but there are some commercial options there that, with a little bit of money, could be used to annotate a medium scale meeting quotes.
So the problem with this work is it's a little too interesting to commercial ventures. If it was a little less interesting, there'd be a little less proprietary.
Yeah, also, because commercial, big tech companies have a lot of resources. So they can make these models perform really well with lots of data and compute. So, there's, and if you've invested all that data and compute into your model, there's incentive to make money off of it. So
Gen AI is going to crash pretty soon, so there's going to be a lot of pizza dough.
Before going to, I think you.
Oh, my question is pretty simple. Like, how data hungry is the model, basically? Yeah.
So, Abraham, you have shown a couple of examples that like two conversations are going up in the same language. So my question is, okay, so we have like languages has two different grammatical patterns. For example, English and Arab. So Arab goes all the other way. How would this kind of full duplex system would support? Because like you can't see the like future, right? Grammar pattern collisions.
I mean, your language models do the big chunk of offloading.
Yeah, because it is like half duplex. You can see the whole sentence beforehand. So this is the question I'm getting at. It's like you can't see future. So that means like you don't know where the nouns come in the full duplex.
I'm not sure I really understand the question.
Okay, so all the conversations that you have in English. So that means like both speakers are using the same grammar patterns. What if like one speaker using like noun to like subject to object grammar pattern and one other using object to subject grammar pattern? How would like full duplex system that you're kind of working on would support that?
Same way. I mean, as long as in the training you have transcripts in that target language, then it would learn to map the target language to the audio way.
So I think what Nipan is asking is like, if you were talking to Yoda,
yeah,
could you have a consistent conversation where Yoda would be? I guess
these don't use syntactic parsers or any of those structures, right? These are more semantic in nature, so you don't need to really care about as long as the attention does the trick for you.
No, there's no semantic or syntactic information here. It's just text. So if you have Arabic text or Swahili text or whatever, you can put it in there followed by the corresponding audio, and the model will learn those associations implicitly. So I don't think that there's any methodological changes that would needed to be made here to support languages with different.
Would this be the same with the mixed languages? Language mixing?
I mean, like code switching, where you speak in two different languages?
Yes.
Yeah, I think so. With enough experience.
Okay.
It's like he builds it, and then there's lots of experimentation, lots of hypotheses. Yes.
Not a lot of high quality duplex data, though.
So here's a question you sort of answered, and you gave when I was thinking of it, you gave a different answer. And I thought, who are you competing with? Are you competing with Moshi? Are you competing? I guess the fact that you're doing that co-op, you're competing.
Who am I competing with? It's a question I don't like to think about because the reality is that any day now, my entire PhD thesis could be solved by Meta or Google or whoever, and then how the hell do I publish? Any day now. I've just been waiting for it to happen.
Published.
And actually, there have been a number of startups that claim to be doing this. One of them was called waveforms.ai. They were trying to solve the audio Turing test, making agents that are completely indistinguishable from human, which includes full-duplex technology. They were bought by Meta in August. So they went dark and have been swallowed up into the abyss. So I assume that Meta is interested in this type of technology, considering that they purchased that company. Qtai, they worked on Moshi, and they actually put Moshi on hold because they found that Moshi was not able, just like remember Jade was saying, not as coherent as frontier models. They found that Moshi was also not as coherent as frontier models because it was trained on this joint audio text objective, whereas frontier models are trained primarily on text, but also with the ability to understand context that contains other modalities. I guess the solution here would be potentially to do that hybrid cascaded thing where you can use a combination of a duplex model for short answers and external model for long answers with COT and tool calling. So right now, they have been working on another system called Unmute, which is a
Unmute?
Unmute, yeah. It's a fully cascaded spoken dialogue system, but it has a very, very, very low latency. Probably feels like, like I can.
Right, Tommy. I was actually going to just kind of, before you give away any more patents, we should just thank you. It's half an hour past. But,
all right. Well, thank you, and thank you so much.